In the preceding clip, we integrated the function f of x, y, z, component of this function in the direction of motion as we moved around the unit circle, and we found that that component was 0, which fit our picture of the curl of f. Now, you recall that this function had a much different picture. The integral around, or the behavior of the function around the unit circle, reversing the I coordinates by making the y negative, had the effect of giving each of these vectors a definite component in the direction of motion around the circle, a non-zero component, and making us suspect even that these directions are, that these vectors are all tangent to the circle. Without actually going through all the details for this function, we can base an integral on what we got previously. The only difference between the two functions is when we get here, our f of x, y, z was negative y times I plus x times j, which would lead to negative sine of 2 pi ti star times I plus a cosine of 2 pi ti star times j. So that using the same parameterization as before, we get f of x, y, z equals negative sine of 2 pi ti star plus cosine of 2 pi ti star. Now this is times j and this was times I. Don't really have room to slip the I in there with the fat marker, but we'll throw one in with the thin marker. Hopefully that's at least marginally readable, but the point is now that this changes sign so that when we calculate our f of ti star dot delta si, this term becomes negative. When we do the dot product, then we have a negative sign times a negative sign, which is going to give us a positive value for the sine squared and lead us to the integral we finally get then the integral from 0 to 1 of 2 pi times what? This time it's sine squared of 2 pi t plus cosine squared of 2 pi t dt. Okay? And very simple, the sine squared plus the cosine squared is 1, so we just have the integral of 2 pi dt. dt evaluated between 0 and 1 is 1, so we just get 2 pi. Now that's consistent with our calculation of the curl of this vector, which had a constant value, which when multiplied by the radius of the circle would itself be able to show us that these vectors are always tangent to the circle. And related to that, I'll just write down a couple of things that are sufficient to prove that. The magnitude of f is the square root of x squared plus y squared. Pythagorean theorem applied to this vector. And on the unit circle, the magnitude of f is 1. Since the integral around the unit circle of f dot ds equals 2 pi equals the magnitude of f times the circumference we find that f is always tangent. Now I've written that pretty small and I haven't completed all of these statements, but that's the crux of the argument that this function is always tangent, which can easily be verified just by taking the dot product of f with a unit vector, with the r vector as we go around the circle. In any case, clearly this vector field appears to have a circulation about the origin, and this integral is an indication of how we can relate that to circulation, how we can relate the function to the circulation, and the fact that the integral is non-zero to the